Hello everyone and welcome to today's webinar on MicroLED analysis. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted, however, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Tamel Buyuk-Lamanli, VP of Technology and Innovation, along with a few of our technical experts, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's talk. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us improve our future events. I would now like to introduce our presenter, Michael Salmon, Scientific Fellow of the Advanced Imaging Group at EAG Laboratories.
Thanks, Rena. Once again, my name is Mike Salmon. I'm the Scientific Fellow for the Advanced Imaging Group here at EAG. I currently work in Raleigh, North Carolina, and I received my PhD in Material Science and Engineering from North Carolina State University with an emphasis in microscopy and surface analysis in 2006. I've actually been at EAG since 2007, so almost 14 years now, 13 to 14 years. And while here at EAG, my career is focused primarily on highly localized characterization and failure analysis of compound semiconductors. So a little introduction about EAG itself. EAG has over 40 years experience in materials testing services. We support over 4,000 clients and 20 plus facilities located in the United States, Europe, and Asia. We are both IP secured and ITAR registered, as well as accredited and certified across multiple industries and markets. We have a business continuity plan that includes a global footprint with disaster preparedness and worldwide redundancy. And EAG is currently owned by our parent company Eurofins, and so we're quite well financially backed. They're a multi-billion-dollar global leader in scientific services, primarily in life sciences type work. So you may not have heard of them before, but a very large company with a portfolio of over 200,000 validated analytical methods. And here's a little map showing the locations of our laboratories as well as business development locations. So over 600 highly educated employees, 20 plus locations, 4,000 different clients in 50 different countries. And EAG as a company, we service the entire life cycle from product innovation and improvement all the way through manufacturing support, failure analysis, and helping with supply chain quality control all the way to litigation support if necessary. And we are on IP secured material testing services lab network. And so we offer full service solutions where we can actually scale from a single job to thousands. So whatever you're in need of analyzing, we can help. So today's talk is going to be on micro LEDs. And so what are micro LEDs exactly? So an LED is stands for light emitting diode. And these are devices that emit light when a bias is applied to them. And thusly, micro LEDs are just micrometer sized versions of this, specifically inorganic LEDs, and typically have dimensions, I think at best these days, about 5 to 10 microns in diameter. And these are crystalline semiconductor-based devices. This is an emerging advanced display technology. So whereas consumer displays at the moment are typically liquid crystal type displays, which are like actually a way to control displaying information by passing light through an active pixel array. In this case, each pixel is made up of an individual light emitting device. And so that gives us really the potential for greatly increased performances with much greater brightness and lifetime, et cetera, over the existing state-of-the-art display technologies such as OLEDs, which also have this individual pixel emission type technology. But the advantage of using crystalline-based semiconductors is that they'll be able to have similar low energy consumptions, but without the image retention issues that OLEDs face, as well as increased ease of scalability for large displays, and being able to put these on transparent back planes, et cetera, for use for augmented reality as well as virtual reality type headsets. So the ability to make very high resolution displays, also transparent, et cetera, is really attractive, along with improved performance and lifetime. And so currently there are various strategies for production of these kinds of small devices. You have direct growth as nanowires and also flip chip technology. And here over on the right side of the screen, you can see here, this is a scanning electron micrograph of a conventional high brightness LED that you might find in a light bulb, et cetera. And you can see here, you're talking scale on the order of 0.5 millimeter, 500 microns by 500 microns. And so now we're really talking about devices that are much smaller here, about 15 microns. So devices about the size here shown between these two arrows. And so by shrinking these dimensions, we actually create a number of different development challenges in terms of making these types of devices. So as these device sizes shrink, so is reduced the efficiency of the devices as well. And this is primarily due to the greater surface area relative to the bulk of the semiconductor going much higher. And so semiconductor surfaces often have very complex electronic and optical properties as compared to those bulk, the bulk materials or within the bulk itself. And they really need to be controlled. And so really these surfaces tend to be a source of contamination and defects that affect the performance, as well as those defects acting as non-radiative recombination sites, so quenching the actual light production. And in a lot of cases, we're trying to scale down the size of the actual device, and it's getting to the point where it's close to the actual electron diffusion length within the material. And so electron holes that are created within the device during operation can actually diffuse to these surfaces and recombine without giving off light, thus reducing the efficiency as well. So ultimately, we need analytical techniques that allow us to understand how to keep these detrimental surface effects to a minimum, and how that's then really a critical aspect for improving the performance and reliability of these micrometer-sized devices. So some of the analytical challenges we have to characterizing these devices repeatably and reliably with such small discrete sizes is that we really want to be able to actually quantify both the structure and the chemistry, but we have finite amount of material. Ideally, we'd also like to measure the corresponding optical and electronic properties of those small volumes as well. And in many cases, we'd like to at least qualitatively, if not quantitatively, try to measure the dopant level constituents. And so ultimately, we have techniques that work on more bulk materials. So for instance, we traditionally do scanning electron microscopy or transmission electron microscopy to understand the structure of epitaxial materials and devices. And then we can use something like SIMS to look at the minority constituents, like the dopant level constituents. But traditional techniques like SIMS for doing these types of high sensitivity analyses fall short for small volumes of materials, such as the ones realized in MicroLEDs. So we need to actually come up with some new techniques to help us better understand what's going on in these small volumes. And one other thing to note is that sample prep methods are always known to be the key to success, and it gets to become even more of a key issue because these samples that we need to analyze now need to be as artifact free, or like I say, artifact known. Like we need to understand what we're looking at when we're analyzing the data, and we have a lot of experience with that, especially for compound semiconductors. But ultimately, the issues that we're facing within micro-LED work are really at the similar scale to a lot of the prep artifacts that are possible. So today, I'm really going to talk about some emerging techniques, mostly microscopy here, available at EAG that are designed for successful micro-LED FA and R&D. We actually have a wide variety of techniques that are available. But today we're going to focus on aberration-corrected scanning electron microscopy, or AC-STEM. We're going to talk a bit about atom probe tomography, cathode luminescence, and scanning microwave impedance microscopy, which is an AFM technique. So on the right here of the slide, you can see the EAG spectroscopy microscopy analytical resolution tool. So this is a nice chart that explains, I guess it shows the wide variety of techniques available for analysis of materials, and then it presents it in such a way that you can understand essentially the detection limits of the technique along with the spatial resolutions that are achievable. And so any of the techniques that fall inside the chart here actually have both of those capabilities. And then we have two regions here. We have just pure imaging techniques below, and then bulk techniques on the right. And so, as I mentioned, using SIMS to look at dilute constituents or dopant level things, you can see that dynamic SIMS has amazing sensitivities down to 1e to the 12 in some cases, but ultimately the spatial resolution really doesn't get much better than maybe a couple microns, right? So at times when you're searching for very small features, dynamic SIMS isn't going to really help you understand what's going on in that small scale. But now maybe we can choose some different techniques. And so we're going to first start off with AC-STEM, which is going to give us essentially the best resolutions in terms of spatial resolutions and the atomic scale, but then also we can combine that with some analytical work or techniques with EELS and EDS, and we can get resolutions down in the nanometer even better. And so here STEM, AC-STEM EDS covers a wide range of length scales, but ultimately it's down here in this ultimate resolution place that we're really interested in using. And this is the kind of technique that's going to give us the best information about the crystal structure in our sample. And so as I mentioned, these micro-LEDs are made from crystalline materials. This is a high angle annular dark field image of a InGaN quantum well in a commercially available light emitting diode device. And this is representative AC-STEM type data. So we can see very clearly atomic columns in this sample here. And then we can take this data, we can take a line profile using this region here and present it on the right, and you can see the atomic corrugation. And then you can also actually see that there's some details about the different sides of the quantum well itself. And so we can actually quantify the surface quality or the interface quality now. So we have this type of discretion, the very highly localized discretion. So here you can see as the indium turns on, we get a big jump in the actual composition. So forgot to mention here, this high angle annular dark field image actually encodes for average atomic number. So it's also known as Z contrast imaging. So here where you see the bright columns, this has indium incorporated into it versus the inner layers here with just gallium nitride. And so when you take the line profile, you can see a change in intensity due to the indium composition within that layer. And you can see when they turn the indium off on the surface side during growth, there's actually a decay of the indium that's slightly different than when they turn it on. And so you've got a less abrupt interface towards the surface. And these kinds of interfacial features are really important to trying to understand the actual operation of these types of devices. And so from that too, modern aberration corrected STEM instrumentation has a wide variety of different detectors that we can use during imaging. I mentioned high angular dark field, so this is giving you Z contrast, and this is the case of looking at gallium nitride itself. And something that's become very important to folks growing device or making devices is knowing the polarity of gallium nitride. It's a polar material, so the 001 direction is different than the 001 bar direction. either being gallium polar or nitrogen polar. And so we can use another detector within the scope called the annular bright field detector, and actually we were able to image both the heavy atom at the same time with the lighter atom, in this case gallium with nitrogen. So in the case of dark field or ADF imaging, we're really only seeing the gallium column. We don't have enough dynamic range within this detection scheme to really image both of the columns at the same time. So we use something called aberration bright field. And so in this case, now you can see the position of the gallium and the nitrogen, and we can clearly identify this as gallium polar material. And so yet another type of detection scheme is something called differential phase contrast. And so in this case, we're using a detector that's actually segmented, so then we can leverage the different segments of the detector, and we can learn something new about the material. In this case, we can map out the electric fields within the sample. This is an example of looking at indium phosphide at the atomic level. Here on the left, we have the Z contrast image, where we're primarily seeing the indium atoms. You get a sort of a hint of the phosphorus being there. But here in this case, then we can also map out the localized atomic scale electric field within the sample as well. And this potentially can be useful for looking at things that have, let's say, multi-quantumals and things like that. We can actually map out the electric fields in a more complex sample as well. So as I was mentioning, not only from a direct imaging point of view, AC-STEM really lends itself to giving us access into composition as well as chemistry of our samples. So in the case of AC-STEM, we're using a highly focused probe of electrons and shooting these through our crystalline sample, and then this gives rise to inner shell ionizations, which give us X-rays that come from the sample, and these are related directly to the elements that are present. So the energy of this X-ray is then related to, let's say in this case, near 1.5 is aluminum. And so we can identify, we get a fingerprint of what's in the sample based on the energy of the X-rays that comes out. At the same time, we can collect our high angle annular dark field image, and we can collect the inelastically scattered portion of the electrons that go through the sample that were giving rise to X-rays, et cetera. And we can collect those electrons that have interacted with the sample and put them through a spectrometer, and this is called electron energy loss spectroscopy. So we're looking for the subtle losses as those electrons interacted with the sample. We can plot that out, and we can once again understand the composition. But in the case of eels, we actually also have the ability to further interrogate these specific edges themselves, and they contain information about the localized chemistry within the sample. And so you typically are going to be using EDS for heavier elements and also for surveying. So if you don't know what's in your sample, doing EDS is a really good way to identify all those things. And then if you're really interested in, let's say, the localized bonding of, say, oxygen in one specific place, a technique like EELS is really great for that. So keep that in mind as we move ahead, and also to remember that these kinds of techniques now are all hyperspectral. So as we scan the sample and create an image at each pixel, we're going to be able to collect an entire spectrum. And so we then develop these hypercubes of data, which we can then go back and process post collection to look for any elements, et cetera, and then study for different mapping of elements or for chemistry, et cetera. Another thing to remember is the EDS has about 130 EV in terms of spectral sensitivity, whereas EELS gets you down to about 1 EV. And so you can see, if you're interested in looking at things that are even more subtle, it's the improved spectral resolution of EELS really gives you access to a lot of information. And so this is just an example showing the type of data that we can get sort of at the extreme. So we can actually acquire atomic resolution Z contrast images. This is an example of a magnesium decorated inversion domain, pyramidal shaped inversion domain in GaN. And so you can see here we've got clearly resolved the columns of the gallium and the gallium nitride, and we can see that the magnesium itself is in EDS is actually relegated to this sort of surface up here in the top. And then down below, we can actually use EELS, looking at a manganese, iron, and cobalt sample, and we can find that there's actually evidence of cobalt anti-site defects here present. So We can't really tell you exactly how much is there, but we can see that it's there. So qualitatively, we can assess this type of chemistry and composition at the atomic level. So this is going a little bit further, like how can we assess the actual chemistry locally? And this is an example of looking at the oxide aperture and vertical cavity surface emitting laser samples. In this case, we have a good control sample versus a couple different failures, and we're taking data near where the failure started, and we can then look at very specifically at the oxygen EELS edge and compare the three samples. And what we're finding is that there's a unusual fine structural detail here at 532 eV that seems to be correlated with the failing devices versus the known good device. And if we then look in the literature, we find information that this seems to be related to a hydroxyl group in the sample. So potentially that there's OH bonds present in these failing samples versus the one that's not. And this kind of chemistry information is available from about a 5 nanometer region within this 25 nanometer thick oxide layer. So very localized chemistry information is achievable. And so really the next thing that we're really working very hard on is actual computational methods to get even more information out of the images that we're creating. And so by leveraging things like AI, and machine learning, we can do these very repeatable measurements of specific layers. And so here, this is the case of measuring a thin coating on the surface of the sample. And so now we can use machine learning to identify that layer, make many measurements, and then plot those kinds of statistics. So we can provide you with both images, we can provide you with images with measurements, or we can even just provide you with statistics of your samples if that's really all you're in need of. But the idea here is that we're effectively able to remove the human error element, and so we can make much more repeatable measurements over time. And to take this a little bit further, we're also working very hard on doing quantitative lattice mapping of these very high resolution AC stem Z contrast images. So this is really giving us the ability, we can pretty much use almost any high quality AC stem image, and we can go in and we can find the centers of each of these atomic columns, and then we can plot each of these columns color coded, for instance, in this case with the C-axis lattice parameter. So here you can see that there's quite a difference in the lattice parameter here on the left-hand side, which is an LMSO layer, versus the PZT on the right. And we can use this kind of information, structural information now, to assess things like strain very locally. We can quantify what's going on at this interface. And we can also look at different defects or phase changes within the sample and have a nice way to quantitatively compare sample to sample. We can present this data in a variety of different ways. Like I mentioned, we can color code the atom columns themselves. We can take an average line profile through this data, plot here on the right, so you can actually visualize here. You can see the lattice parameter on the left of LMSO, and then you can see how we get into a strain PZT region on the right as it relaxes back to its bulk parameter. We can also then plot, the entire all of the data that's globally, and you can here clearly see the two histograms at LMSO and PZT, and we can understand something about the shape of these peaks as well as going on. We can use this to directly compare sample to sample. So this is really where things are headed. So being able to really get good quantitative numbers from this data and then relate that back to things like EELS and EDS. So you have compositional analysis, and then you can combine that with this very highly localized quantitative measurements of the lattice parameter itself. So good feedback, internal feedback for what's going on. And so from there, I'm going to talk a little bit about atom probe tomography and the benefits of being able to then have greater sensitivity for more dilute constituents, while also being able to look at the structure of the sample in a very localized way. And so for atom probe, You can see it sits up here in this upper left-hand corner of the chart. So we've got pretty good detection limits down to about 1E18 for specific elements. And ultimately, you know, the resolution gets down into the nanometer scale. And so here on the left, you can see this chart and how it compares to things like SIMS or TEM eels. And so you can see it's got very improved chemical sensitivity, spatial resolutions comparable to TEM eels, and the analytical area is fairly small. But what it does give us is three-dimensional data, which is unlike any of these other techniques. And that three-dimensional data is a very powerful way to assess these kinds of structures and exactly where things are. And like you can assess them in ways you couldn't before. So how do we actually make an atom probe tomography sample? So we use a lift out method similar to making a TEM lamella. We first bulk it out, we lift it out, and then we put it on a very special needle, and then we trim it up. And then effectively, we then do some annular milling to effectively make a very sharp needle. And in the end, that we have a needle here with a tip apex radius of less than 100 nanometers or so. So we're going to take this very sharpened needle of your sample, and we're going to put it in the instrument. We're going to bias it from anywhere from 0 to 10 kV. We're going to hold the sample in cryo conditions from anywhere from 25 to 80 Kelvin. And we're going to then extract using these high electric fields, in addition to using a pulsed laser to effectively help ionize each of these atoms off of the tip one at a time. We're going to then accelerate them down through the spectrometer, and we're going to collect them with a time of flight type spectrometer that also has a spatial position sensitive detector. And so then we're going to effectively deconstruct this needle and then capture that in a data set, and then have a three-dimensional mapping of where all these atoms came from within the sample. And so this is very useful in the sense that we now have this three-dimensional data set that has all the atoms that were present in the tip itself, and then we also know what element they were, what element they were by this time of flight, right? So we can mass separate and then understand what element by how long it takes to travel through the spectrometer. So then we get position plus composition essentially. So this is a first example is to show you how, like looking at epi material, for instance, this is magnesium implanted GaN, how typically we would use something like SIMS to look at implants, and you get profiles similar to this for varying different doses. In this case, we're going to look at this 1E16 annealed sample. And if we take a conventional TM bright field image of the sample, we see that there's like actually quite a lot of structure within the sample, a lot of damage. And in this case, there's a lot of magnesium decoration along these defects within the sample itself. And so for doing atom probe tomography, we're going to make our needle out of this region here in the sample. And this is the kind of result we end up seeing. So we get this mapping of gallium, nitrogen, and magnesium within the tip itself. This here is the overlay of all three. But then we can actually take lateral distribution slices here, in this case, 3 nanometers thick, and observe it along the C-axis, like the vertical axis. So if we're looking top down at the needle, now what we can see is if we plot the magnesium here, we actually see that there's ring-like accumulation of magnesium within each of these 3 nanometer layers. So these defects that we're viewing in cross-section actually end up having this unhomogeneous gettering of magnesium within that structure. And that's very interesting in terms of understanding what's going on within the sample. One aspect to understand is that with APT, it can often be difficult to know accurately the magnification for each sample. And so even though it can determine the chemical composition and 3D structure very effectively, it can struggle at times to determine the size of the feature accurately. So we can actually utilize another technique, AC STEM again here, but in plan view, so we can make a sample to mimic our 3 nanometer slice in the APT, and then we can we can then compare the two, and we can actually see we have very good agreement in terms of the topology of this kind of defect. And then we can also understand the size a little bit more accurately from the plan view AC STEM work itself. So using multiple techniques together is really the way to get the full picture of what's going on in your sample. And so ultimately these two agree well, and we agree that the magnesium accumulates at the fringes of these planar defects. But it is important to realize too that this image here looks a little more complex, and that's because ultimately with APT we can actually look at a thinner amount of material in post-processing. So in this case, this is a 3 nanometer thick layer. It's very, very difficult to make an AC STEM sample that's on the order of 3 nanometers without any sort of damage or contributions from surface effects in the image. And so here, this is a little more complicated looking than the atom probe. So the atom probe gives you a bit better depth discretion in this case. So now how can we apply this to micro LEDs? We can use then atom probe to look at a epitaxial structure like this in a micro LED. We have positionability, like we can effectively select where we want to go to make the sample. And that's really just limited by the resolution in the SEM and FIB itself. So that's like nanometer location or precision to go after things. In this case, we're going to look at this kind of epi structure here, and the atom probe can be used to then provide dopant distribution in 3 dimensions as well as morphology. We get to understand a little bit about the aluminum concentration in the blocking layer. We can then also look at indium dispersion in the quantum well, as well as the indium concentration across the quantum well interfaces themselves. And so this is a typical STEM cross section of this device structure here, and then as you can see in the red dotted lines, this is going to be our representative atom probe tomography sample that was made, and here's our 3D model that we get from the sample itself, and we can then utilize this to identify the different regions of interest within the sample that we want to further look at a little more closely. So here, if we zoom in on this the multi-quantum well region, we can then create a slice out of this data set to then very specifically look at this quantum well region itself, and we can make things like composition profiles of the indium from this region, where we see that there's actually quite complex indium distribution throughout this layered structure. There's actually some indium here up above on the P side slightly. You've got a couple like a stair step kind of feature with each quantum well, the first 2 quantum wells, and then the 3rd quantum well appears alone. And then as you can notice, the background here up in the upper part of the P in the gallium nitride area up here, you can see we get just, there is actually sensitivity to see this kind of low levels of indium as well, which is really, really useful. And so then aspects of the data set that we have, now we can actually interrogate, for instance, the roughness of an iso concentration surface within that each of these quantum wells if we want to. So we can look at the actual roughness of this very specific indium, looking for segregation, things like that. But we can also look for the dopant within this device up here in the P algan as well, and the superlattice. But speaking of the dopants, so the dopant tends to be a very important thing that people are interested in, especially trying to understand it in these very small volumes of material. And so this is a second example of looking at doping in a P algan region of a sample. And here, once again, we can take slices out of the APT data and then present them in X and Y. And so what we see is that there's actually clustering that's occurring within the doping within this. That clustering can be very important. And so the idea here is like, so we can actually get an idea further, we can pick specific 1 atom percent iso concentration surfaces that go around these clusters, and we can analyze how the clusters like are varying in concentration within them, right? So we can actually see that there's a change in concentration from inside to outside. So it's actually not a constant. It's not like it's a precipitate, so to speak, but you're getting this very specific type of clustering. And then this has the sensitivity to be able to tell us something and put a number on that to get an idea of how that concentration is changing versus spatial across different length scales. And so ultimately the dopant concentration is changing monotonically from outside to inside the cluster themselves. And so this is a very unprecedented way to be able to look at these kinds of materials and to give us insights into what's controlling the overall performance of these types of devices. And so from there, that takes us into looking at another technique called cathode luminescence. And so cathode luminescence is the collection of light or the emission of light from luminescent samples and as using electrons as the excitation. And so SCM it sits here in the chart, so it has fairly good spatial resolutions along with fairly good sensitivities. So on the order of top SIMS types of sensitivities, so not the best, but also much better spatial resolutions though. And so cathode luminescence, as I mentioned, is the light that's created from the interaction of high energy electrons with our semiconductor sample. So as we inject electrons into that sample, electron hole pairs are formed, and then they recombine and give off light. And this is just one of the signals that we can collect. Typically in an SCM, which is the type of instrument that we're using here, we also collect the secondary electron signal. So that gives us some information about the surface of the sample that we can use to register our light emission. And in this case, this is a very cutting edge system that we have here in the lab. This is made by Adalite. It's a custom SCM column with an integrated optics within the column itself. So this gives us really the ultimate in signal to noise by having the highest collection efficiency possible, having this large mirror integrated within the column itself. And then we collect with various different pixelated cameras, an in-gas camera for doing red to far red, and then we use a silicon CMOS for doing visible light. So we're collecting similarly to EELS and EDS nowadays, we collect hyperspectral data. So what causes changes in the CL signal of luminescent materials? In this case, we're looking at band gap variations due to quantum confinement, alloy fluctuations, things like doping, concentration, strain. Also structural defects create changes which influence device performance, as well as potentially having some interesting quantum mechanical behaviors. And ultimately here on the left, you can see as we generate electron hole pairs in the sample and we create across the valence band and conduction band, these electron holes recombine across here, and you've got a couple different scenarios. In this case, we've got some interband gap states created by different defects, for instance. And so in some cases, these electron hole pairs can reside here and give off a variety of different wavelengths, which are then related to those transitions within the material. And we can map those out and get an idea of what's going on. And so typical applications for CL would be for defect detection and characterization, including things like threading dislocations, stacking faults and inclusions, and as well as composition metrology, failure analysis, nanostructure characterizations, etc. This first example is just looking at how to calculate the threading dislocation density. We can use the band edge and GAN, and we can do a monochromatic CL scan here. And then each of these dark spots is related to a single threading dislocation. And we can count these in an automated way up to about 5e to the 9 dislocation density. This example shows 3e to the 8 or so. And it's fast and non-destructive. And so, like I mentioned, we take hyperspectral data, so we can take this data set, and as we scan the sample, we collect the spectrum in each pixel, and then we can do post-acquisition digital wavelength filtering here. Yeah. We can do post-digital wavelength filtering to look at different structures within the sample. In this case, a couple different basal stacking faults have emissions at very specific wavelengths, and we can then map those out. And this kind of information, we can, count how many basal stacking faults per unit area, et cetera, or we can use it for very specific site cross-sectional stem samples to understand further how it's affecting our devices. This is an example showing how we can use CL to understand doping changes in the sample. This is a GAN hemp structure. And so here we can see that there's a vertical threading dislocation that's causing disruption of growth and then integrating the carbon differently, the carbon dopant differently around that dislocation. So that has carbon content similar to the unintentionally doped surface layer relative to this carbon compensated layer here, showing up as a potential short for this device. And this device was showing leakage at this site in particular. And so here we're able to correlate a change in that doping concentration with performance changes in the sample itself. This is an example of looking at quantum dots in nanorods, for instance. So we can see that you can get very specific spectral signatures from these quantum dots relative to the gas core of these kinds of structures. So we can then utilize this to count numbers of quantum dots, et cetera, and understand something about the differences between two very, very small samples here on the order of a couple hundred nanometers in diameter. And so that takes us to our last technique, which is scanning microwave impedance microscopy. So this is an AFM-based technique now, and you can see that it gives us access to electrical active dopant and mobility information within the samples, and then gives us spatial resolutions down to a couple nanometers and typically around 30 nanometers or so, and very good sensitivities as well. I'll refer you as well to this webinar that was previously presented for more information about it. And here I'll briefly go over a few of the aspects of this technique. So scanning microwave impedance microscopy, or SMIM for short, is a near field AFM technique wherein microwaves are sent through an AFM cantilever to probe local electrical properties, i.e. the permittivity, which can be converted to capacitance, and conductivity with nanometer scale resolution. The measured properties themselves can be converted to type of charge carriers and concentration for semiconductor materials. SMIM enables us to measure both surface and subsurface information, and that's really one of the most unique properties of this technique. You may have heard of scanning capacitance microscopy in the past, but this is really a more modernized version of that, and gives us access to quite a bit more information, useful information. Essentially, we're gonna use a specialized probe that's coded to reduce the background capacitance, and then that improves really both the electrical spatial resolution as well as sensitivity. And essentially, we're measuring the intrinsic capacitance. SMIM is compatible to measure a wide variety of material systems, ranging from dielectrics to semiconductors to insulators as well. So before we dive into it too far, it's an AFM-based technique, and so the most basic mode for AFM is known as contact mode, and this is the basis for many electrical techniques like SMIM. And the schematic here on the slide shows the main components and configuration of a dimension, like a dimension type AFM instrument. And the probe consists of a springboard cantilever and fine radius tip, and it's attached to a PZT scanner, and the scanner allows precise control of the position of the tip relative to the surface of the sample. We're going to use a laser reflected off the back of the cantilever into a position sensitive photodiode, and that's going to give us some information about how the cantilever is bending, and then we can create feedback with the PZT to keep in a continuous amount of force on the sample effectively as we scan it. And this is going to help us then effectively map out the actual topography of the sample itself. And so in the case of SMIM setup, we're going to use specialized electronics by Prime Nano in our case, which we put a 3 gigahertz signal through a fully shielded path. The microwaves create a near field electromagnetic fields at the tip apex. These interact with the sample beneath it, and the reflected microwave signal is then processed through the electronics, and the output of the imaginary and real component of the tip sample admittance in the SMIM-C and SMIM-R, which correspond to the material permittivity and conductivity of the sample. As the probe scans over the sample, it creates an image showing this relative to the topography image. Furthermore, an AC voltage can also be applied, and we can monitor the changes in SMIM signal to relative to the voltage applied, and then this gives rise to the DC DV and the DR DV. So ultimately, though, the idea here is we're able to measure locally the conductivity of the sample and the permittivity at the nanoscale. So this is an example of an IGBT defect localization that was done. SEM here in the background is just for representational purposes, so you can get an idea of the overall device structure itself. The SMIM-C image on the right can show the defects in both the insulator as well as the gate region. And it's important to realize too, you also get information about the doping in the emitter region here, and you get details in this that SCM isn't able to show us. And this kind of doping information is monotonic with log doping concentration, unlike conventional SCM or DCDV, which then allows for a direct interpretation of the low doped versus the high doped areas qualitatively, as well as if you use calibration samples, then you can get an idea of quantifying this kind of doping concentration, which is very useful. And so lastly, a unique aspect of SMIM is being able to understand and evaluate buried structure as well. So in this case, this is an example of a planarized silicon nitride layer on top of silicon oxide islands. And both of these materials are both insulating, but they have almost a 2x permittivity difference. And so in this case, the SMIM, although the AFM sees really no difference in the topography, the SMIM clearly identifies the regions of silicon oxide within the silicon nitride. And so this kind of information may be kind of important, especially in dealing with, let's say, complex surface structures that might be present, like say on your micro LEDs. So you can actually get information from below just the surface itself, which could be very useful. And so with that, I'm going to finish up. And so why choose EAG? There are several reasons, but I think it's really important to state right at the top that client confidentiality is really the core to our business. We're a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even your most challenging materials and engineering related issues. And in light of the pandemic that's affecting us all right now, I do want to stress that EAG is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local governments, as well as the CDC. Currently, all of our locations throughout the world remain open, but we may have limitations on customer visits. And as this is a fluid situation where we are operating a laboratory at reduced capacity, we can also transfer your samples to other locations if necessary. So we encourage you to discuss all your options with your sales representatives.